is the first one. Okay. And now I start to explain my problem-solving process. For the second example in the section 2, we know that the date of the survivors in the new treatment and the old treatment is the same. Okay, is there? The no survival rate is 40%. Since the question A, B, and C is the same, and all give the beta distributions. So my solution is find the corresponding distribution function first. Okay, here. Consider theta subject to beta and the parameter alpha and beta. So, and then plug in the numbers to get the answer. Firstly, and let the joint distribution is the probability y given theta. And then the prior distribution is here. The probability theta equals to 1 over beta distribution and multiply by theta to the power alpha minus 1 and okay, the probability theta given y proportional to p y theta multiplied by p theta. And obviously this is a beta distribution. So finally I get the theta given y subject to beta. The parameter is t plus alpha and n minus t plus beta. And this is posterior distribution. And easily to get the posterior mean is E theta given y here. And so I get the answer A, B, and C, and like this here. For question D, because the theta subject to uniform distribution, easily I can get the p theta equals to 1. So the joint distribution of simple y and parameter theta is here. Okay, and then the distribution of simple y is my. Okay, and finally the posterior distribution of parameter theta is like this. Okay, and finally, question D is there.
Okay. Can you show me C just now?
Sorry.
Question C. Question C.
C.
Right.
Yeah. easier?
Oh, no. I'm like thinking like, oh, okay. So the question, D, or C, sorry, the C is okay. C is, okay, all right. Actually, for D, right? For D, you don't have to do it. You don't have to find the marginal, right?
Marginal distribution?
Yeah, you don't have to.
Oh, okay.
Okay. So because remember, right, to get the posterior, you just multiply the likelihood with the prior. So the prior is uniform 0, 1, right? It's 1. I mean, the PDF is 1, right?
Yes.
So what happened is you just multiply your likelihood with 1. That's it. So you don't have to integrate actually.
I know.
So you're working, you are doing it like it's not wrong. It's just like it's not needed. So you can just multiply. You can just multiply your likelihood, which is your theta 6, 1 minus theta power 9, theta power 6, 1 minus theta power 9, right? Multiply by 1. That's it. So your likelihood is actually, so your posterior is actually proportional to your likelihood because your prior is 1. So you go down. Go down the next page. Right? So you can see over here, right? Yeah. So you don't need to multiply because you don't need to remember, right? Because you don't need to find your my because my is a constant. Right? So it's just proportional. Yeah, it's just proportional.
Oh, okay. Okay.
So that's why it's not wrong. It's just like not necessary lah. So you are doing extra work. So you just multiply your likelihood with 1. That's it.
Oh, okay.
So you get the kernel of a beta. So it should be a beta. So actually you get beta 710. Yeah, you will get beta 710.
Yes. Okay.
So likelihood, yeah. So your posterior is your likelihood multiplied by 1. That's it. I mean proportional lah, proportional. Your posterior is your proportional to your likelihood multiplied by 1. Okay. So you don't need to find your. I mean, you get the same answer, but so you don't need to find. You don't need to integrate actually.
Oh, okay.
Okay. All right. So it's not wrong, but it's just like not needed. Okay.
Okay.
All right. Thank you. Okay. I think. Let me see.
Hello, it's me. Yeah. The question E is me. Right?
It's you.
Actually, I'm not quite sure how to do the 5. I don't know. It's a little weird. This is the first. This is the first way I did this question, and this is another kind. I don't know which one is right. Not quite sure of this question. Yeah.
Yeah, actually, question E is you need that's why I give only 1 because you need there's a trick to that. You have to integrate actually. That's why it's the hint, right? You can see in the question there's a hint, right? Because because you need to use it the hint. Yeah, in the question. Wait, let me see.
I think the question is oh, sorry, this is not this one. Yeah. This is the question here.
Yeah, right. So there's a hint, right? So the hint is actually for question D.
The hint is for question D.
Yeah. So the hint is for question E. Yeah.
Yeah,
The hint is
I don't know how to use it. Because I used the R to test the answer, but I still not sure which way is the right way.
yeah, can you show me your answer again?
Uh,
Or
I have two kind. The first one is I'm not sure it's right or not. It's simple because when the theta is between 0 and
yeah,
0.5,
yeah,
the
it's wrong.
positive theta is 0 and then it's 1. So the exception is very easy. But if
Yeah,
I
that
take
one
it
why
another.
not correct. Yeah.
But if
The
I another thought, I think it's quite complex, but I don't know which one is right.
yeah, because you have to find your C. You have to find the constant C actually. Because yeah,
okay,
because it's not a proper PDF.
PDF. Oh
It's
yeah.
not it's not a proper PDF. So actually you have to find the constancy such that the is actually a proper PDF. Actually,
So
that the
you need to find the
because
constant.
yeah, because
Yeah.
when you want to find because it's not a beta distribution.
Yeah.
Because you have they have two parts, right? They have two parts, so it's not a beta. It's like a mixture distribution. So actually, what happens here? The hint is given so such that you use it to find the constant C, such that it's a proper PDF because it's not a beta, so it's a different distribution. It's okay. It's okay. I think it's alright. I can discuss that later. It's okay. It's okay. It's
Okay,
alright.
so I can close my window.
Okay, yeah, can close. Alright. I can discuss that later. Alright. Alright. And then so next we have
It's me.
oh yeah. Okay.
Let me share my screen. Okay. So for this question, we have random variable y from the normal distribution, and we are only interested in the mean. The variance is already known, and we were given this prior distribution. So for A, we wanted to find the posterior distribution, and the question has already given it to us. We just need to show that the prior distribution is this. It looks a little bit complicated, so I think it's easier if we write out the kernel first. So this is the kernel of the normal distribution with the parameters plugged in. And I simplify it a bit. Note that the mean doesn't depend on data, so we don't have to include the mean square in our kernel. And to find the posterior, we need the prior and likelihood. So for prior, we can find the kernel using a similar method. So we have this as our kernel for the prior, and then for the likelihood, it's proportional to the product of the density function for yi to yn. And after simplifying, we will get this. Then we can multiply them together to get the posterior. So this is what we have, and let us take a look at like how we want the final kernel to look like. So it's something like this. So what we need to do is like we need to reorganize the terms here, and I think we can factor out this negative and over 2W sigma square. And then like we group the terms in the square bracket to have one group with the factor theta square and another one with -2 theta. And after doing some algebra, and if we like multiply this term and this term together, we'll actually get 1. And in the process, we'll need to expand the W. Then we can see that they will multiply to 1. And then for the multiplication of this term and this term, is also similar. We just need to rearrange the terms, and then we'll need to expand one of the W to get what we want, which is like this term here. Oops. And then, so we have shown that the kernel is something like this, and this is the kernel for the normal distribution with this mean and this variance. So this is question 2A. Then for 2B, we want to show that the 95% posterior credible interval for theta is actually equivalent to the 95% highest density region. We can make use of the two property of normal distribution. First is the symmetry property. So normal distribution is symmetric around the mean. So we know that the lower bound and the upper bound has the same height at the density. And besides that, normal distribution is unimodal. So anything on the left-hand side of the mean is monotonically increasing, and on the right-hand side of the mean is monotonically decreasing. So we also know that everything on the left of the lower bound is lower than everything within the lower bound and the mean. And we also know that everything on the right-hand side of the upper bound is lower than everything within the mean and the upper bound. So we can see that the density inside the credible interval is always higher than the outside. So these two intervals are equivalent. Yeah, and that's question 2B.
Okay, I think I will also discuss this later, because you have to add in a bit more. I see in because this one you have to actually show the probability actually. You know that the probability kita actually you can show that directly using the PDF. But it's okay. This is like halfway. But when you see the density inside is always less than outside, then actually you have to show that using the density.
Okay.
Yeah, it's all right. So it's like halfway lah. So I think I will also discuss this later.
All right, I'll stop sharing.
Okay, thanks. Okay.
Yeah. Can you guys see my screen?
Yeah, can you make it bigger?
Sure. Yeah, my part is for the 2C. Suppose we wish to make a prediction about a future observation that show that the predictive distribution is like Z given Y, then follow the normal distribution with the mean, this one, and the variance, this one. So by using the law of total probability, Z given Y, we need to integrate, average all the d theta, the theta for the joint distribution, that Z given theta, and then data given y, the posterior distribution. So where the z given data is follow the, because in the definition we assume for the rest of the data is follow the y. So for the question 2, the y is theta and the sigma square. Then we simplify the terms this term to be k, this term to be k. So this is the marginal, this is the PDF for the dz given theta, and this one is a posterior function. After that, we do like a proportional, then we remove all the constant out. Then we just to expand the bracket, the square, then we solve it, then we move around. Then in this case, because we are integrate under the data, so we can bring the z outside the integral function, and we can hide somehow like hide the k square here the constant value. Then we just hide it first. So after that, we just to play around with the algebra equation, then we move around until this part. So as we can see until this part, right, it seems like we have a kernel of the normal distribution with the mean and variance, those things. So we just add in the constant here. Then we just to divide it outside. So in this case, this one is the PDF of a normal distribution with the mean kn plus wz divided by w plus n with the standard deviation w sigma square over w plus n. Trust this one will be equate to 1. We'll integrate to 1, so we can just ignore this. So next, in this part, we just copy down and we do our things here. So this one is just to algebra equation. And then we bring back our, from the initial part that we proportion 1, then we remove all the constant thing. So we just add back 2 constant this thing and also the k value, k. Here, then we just do the algebra again and again. Then we get this one. So hence the z given y, it follow the normal distribution with mean k. This one is a mean k, and also the parameter, and also the sigma square here, this part, and also this part is the same. So hence it's proven that there's given z given y is follow the normal distribution. Then I just expand and bring those k inside, then this part and this part, so it's equate with the yeah, that's all for the questions 2C.
Yeah, thank you, Mr. Kim, for your hard work. So if you've done it, you try yourself, you know already. I mean, everyone else, you know how hard it is actually. Okay, thank you. And then
It's me.
okay,
Can you hear me right, doctor?
yes, I can.
Okay, wait. Let me share my screen. Okay. Can you see my screen?
No.
Is it sharing? No, it's not sharing. Wait. Share screen. Share screen. Okay. Can you see it now?
Yeah.
Yeah.
Yes.
Okay. Yeah, great. Okay. So, yeah. So for questions 3, right? So we are given the
Using your tablet or what?
I'm using my iPad.
You have to turn it.
Pusing.
Because
Okay.
yeah, because I see that's what I did with my tablet also. Because if you speak menegak, dia is small. The screen will look small.
Okay. Yeah. Okay, so I can start.
Yeah. Okay.
Okay. So we are given the prior distribution is beta for 4, and the theta, right, is the probability of a coin that will yield a hit when spun in a specific manner So the coin is pumped 10 times, and we are only told that the number of heads that it appears is less than 3 times. So in question A, we are going to find the posterior distribution up to proportionality, and also show that the normalizing constant K is given by this one. Okay, so now here they give a little hint, which is the distribution of the data. So if Y is the number of heads obtained, right, then the distribution of the data should be 1 is the event that Y is smaller than 3. So let me go to my solutions. Okay, yeah. So can see, right, doctor?
Yeah, can.
Yeah, okay. So since the prior distribution is given by beta, so then we can write the prior distribution is proportional to this. Okay, and the data is between 0 and 1. So now we know that Y is the number of heads obtained in 10 spins, right? So which means Y follows a binomial distribution, and the M is equals to 10. And because we were told that the number of heads actually appear less than 3 times, right? So the distribution of the data that we want to find is actually the cumulative probability of Y less than 3. So I just use Z over here. So Z represents the events that Y is smaller than 3. So we can just write it out, and then I can obtain this. Okay, so this part represents Y equal to 0, Y equals to 1, and Y equals to 2. Okay, so then the likelihood of data given Z is this one. So L theta Z is proportional to this part. So then now we can find the posterior distribution up to proportionality. So it's given by this. And the data over here is between 0 and 1. So because this is proportional, right? So when we multiply the right-hand side with some constant K, then we get the equality. Okay, so now because the posterior distribution, it has to be a PDF. So then it follows that if we integrate over the admissible range of data, then it should be equals to 1. So then the normalizing constant K can be found as follow. So now if you look carefully, these 3 terms over here, right, they actually follows, they resembles the kernels of a beta distributions. So actually this part we can rewrite it, make it become a PDF of a beta, and then we can get our normalizing constant K over here. So I lazy to write out the whole PDF, so I just put F theta 1. So the F theta 1 is the PDF of a beta distributions when the A is equals to 4 and B is equals to 14. So similarly for the F theta 2, the distribution is this beta. And for F theta 3, the distribution is the beta 6 and 12. So then, because this part, right, when we integrate the PDF over its admissible range, so it becomes 1, 1, 1. So then we just left with this thing. So now, I think most of our people knows that the property of gamma functions. So first, I have to move the gamma 18 to the right hand side first. So then, if you look closely, in the first term, right, we have gamma 4, then second term gamma 5, and third term we got gamma 6. So which means the gamma 5 and gamma 6, we can actually make it become gamma 4. And then we got gamma 14, gamma 13, and so gamma 12. So the gamma 14 and gamma 13, we can make it become gamma 12. So, and I just use the property of gamma function, then I can show the normalizing constant is equal to this one. So if I'm not wrong, the posterior distribution is actually a mixture of 3 beta distributions. And the 3 beta distributions, right, is beta 4, 14, beta 5, 13, and also beta 6, 12, with their respective missing weight is these 3. Okay, so then if we want to find the posterior means, right, so we can actually use this formula. It can be proven. I just use it straight away. So this one is the weight. So this is the missing weight of the first theta 1. So the theta 1 is follow this distribution. So I just put in all the values in. Then I can show the mean is 0.305. Okay, so then for C, we need to find an approximate 95% credible interval for theta given Z for the posterior. So we are given the value of the second moment of the posterior, so it's equal to 0.105. So we can find the variance, which is equals to 0.011975. Then we can approximate the posterior distribution with normal, and then we can find the credible interval is this one. So how I get the credible interval is actually I just put it into the probability, then this part it has to be equals to the 2.5 percentile, and the upper bound is the 97.5 percentile, so it's 1.96 and also negative 1.96. So then just do some algebra and can get the answer. So yeah, that's all.
Sorry, can you show me your credible interval again?
Yeah, this part.
Your estimate, yes.
Okay, can you see?
Yeah.
Is it correct?
Oh.
I'm not sure whether
Okay.
correct.
Yeah. Yeah,
okay.
it's correct. Yeah. Because
Okay.
just now I didn't see it because it was your writing is too cute, too small.
Okay. Yeah, okay.
Right. Yeah. So
Okay.
I see. Yeah. Okay. Yeah.
Okay.
So yeah.
Then
So okay. Good
for,
work, Mr. Talk. Yeah, I think
okay.
you did it. Okay, so for anyone
Thank you.
wondering, this is actually the same trick that we can use for question 1E actually, meaning that we have to find the constant, right? So this is where you have to integrate and get the constant. Okay, so wait, I'll need to change to my tablet before I can discuss the answer. Okay, first you can hear my voice, right? Right? You can hear it? Right, class?
I can hear, but there's a bit of noise.
Oh, okay. It must be my fan. Sorry about that. Is I don't have an aircon, so right. I think I need to move it further away from the fan. Okay. Hopefully that's like clearer. Okay. Wait. I need to. Wait. Sorry, not this one. Oh yeah. Okay. Right. Right. So you can see it. Okay. Right. So for question 1E, right? For question 1E, question 1E, right? So if given you have your prior, so you have your prior is because it's a mixture. So actually you will have similar with question 3 just now, right? You have your posterior is actually a mixture, so it's not really a beta. So similar to just now, it's going to be a mixture of beta, right? So if you have your posterior, okay, so it will be likelihood multiply by posterior. Okay. So then you have, because you have 0, right? Right, you have your 0 in the first part. So what happens is actually you have your, this one, because this is your posterior. Well, it's not mixture actually, because okay, it's not mixture, but it's the range is actually from 0.5 to 1. So that's why, okay, so it's not mixture, but it's actually going to be your theta is actually from 0 to 5 to 1. So it's actually not really a beta. Okay, so then because the 2 is the constant again, so you can actually just use this part. Okay, you have 0.6, so theta power 6 to 1 minus theta power 9. Okay, so what happened here is, as I say, right, because this one is not a beta, but it's not it's not a non-distribution. So what happened here is you have to find the constant. So because they integrate, because to make it a proper PDF, you have to integrate to 1. Okay, so and because the theta is from 0.5 to 1, so that's why you have to find, you actually, basically, if it's a PDF, so you have to integrate from the limit. And because it's a proper PDF, but you don't know, because okay, if you have an equal sign, if this is equal, right, you have to have a constant here, right? So a constant time this is actually equal to integrate to 1, right? So you need, so now what happened here is actually you need to find this constant. What is the value of this constant, right? So if this is proper PDF, if you integrate, it should be integrate to 1. Okay. So what happened here is, this is where you you need to find, okay. So the trick here is using the hint given in the question, right? Okay, so using the hint given
Hello.
Hello?
What's happened?
Prof, we cannot hear you. Hello, doctor. We cannot hear your voice.
Sorry, class. I don't know why it keeps disconnecting. I was writing and I don't know what happened actually. You all can hear me now, right?
Yep, yep.
Yes, yes.
Yeah, so sorry, I don't know what happened. So I think so because sorry, because I'm writing on the pad, so I cannot see the screen actually. Right. So if I'm disconnected, you have to because my computer doesn't have a speaker. That's a problem. So I cannot see the screen and I cannot see my tablet at the same time. So that's why I can't. So I don't know. Okay, where was I connected actually?
1E to find the constant.
Okay, I know, but is it from the start? Was it disconnected from the start or from in the middle?
I think it's just 30 seconds after the start.
Oh my god, I've been talking to myself again. That's why because just now someone said that you can hear my fan. So actually I moved to further away from the screen of my computer, so I couldn't see my computer actually. Okay, all right. So basically I've been talking to myself. Okay, all right. I'll just I've been talking again to myself, so I'll just share. I think I've written a lot. Okay, let's just go over again. Right, so I have to do it like this. Okay, I see I've actually written a lot. Okay, so just going through again just now. Okay, so I said that to find the constant, right? Right, to find the constant. So you find the posterior. So you have to multiply with the prior. So this is your posterior with the constant k, right? So you have to use the constant. You have to find the constant k. So you have to use the hint number 1, right? If it's beta 710, then the probability of x bigger than 0.5 is 0.227. Okay, so then you can manipulate. So you get this part. You get this line, right? And then it's a, and then because you want to find, this part is a PDF, right? I just read, right? So this is a PDF, right? Because you want to find it. So this one equal to 1. Okay, and this is actually, and if you move around this one, right? I just move it because this one is sorry, I just move it to this one because I just move this to here, right? I move this constant to here, I get this, right? So this one equal to this, and then multiply by k on both sides. And because this is a PDF, so this one equal to 1. So this thing will be equal to 1 also. And that's how you can get your constant k. Okay, you get your constant k. So this is your constant k here now. Okay, and then if you multiply your k with your this part, then it will become a PDF. And it's exactly, it's not a beta because it's your theta is from 0.5 to 1. So it's not this one is not a beta distribution. Okay, but we use the fact, the beta, the property of the beta. Okay, so you have your k now. So just only half of the part. You have half of the part, right? Okay, so then you want to find the mean of theta, the posterior mean. So the posterior mean is actually your theta multiplied by your posterior. So you have this one with the k. I just put k again because it's too long. As question 3 is too long. So this is your k now. You want to find the expectation of this one. So you use your second hint, right? Use your second hint. So you have your beta 810. The probability of beta 810 is actually bigger than 0.5, is actually 0.315. So this is the PDF of your beta 810, right? I mean the beta PDF and the probability of x bigger than 0.5 is this. Okay, and then you have your into this part, right? And then you have the mean of your, so you put the one that you want to find is actually this. Okay, this part theta given y. So this is your part, right? So this is where I stop. Actually, I just turned around and I saw that my screen is blank. Okay, so you have this. Then you have the posterior. I mean, so actually, basically, you have to put this in, right, to integrate to 1. So originally, your mean is this. This is your mean is this only, right? Okay, multiplied by this function. Okay, so then we add your constant, multiply there, and then multiply with the tau 18, and then tau 8, tau 9, tau 10, sorry, and then multiply by your theta 7, 9, right? So this will actually integrate to 1. Wait, I think I'm missing something, which is, wait, I think I have a 0. Oh, sorry, it's not integrate to 1. Sorry, this one, because this is from 0.5 to 1. So this is actually 0.315, right? Because this is this probability, right? This is actually this probability 0.315. Okay, So you have here K, the long K, because no, it's too long to write. 10 and then tau 18 and then multiply by 0.315. Okay, and then again using the gamma function, right? Open the gamma function, multiply by K, so on. Too long to write, and then you will get around 0.57. Okay, right? So yeah, after missing a lot, so okay, so this is just showing you, right? Meaning that the hint is given for, actually the hint is given for question 1E. Okay, so you have to take find the fact that the theta is part of the beta distribution, but it's not a beta distribution. So there's a hint given is to find the probability of theta. If it's beta, then x bigger than 0.5. Okay, then you get the answer. All right, so any question about 1E class? No question? Right, sorry, my writing is not very good because I'm writing on my lap because I cannot have to face the screen. Is it okay, class? Class, are you okay? Any question about question 1E?
No question from me.
Okay, thank you. Okay, so for 2B, right, I was saying that for 2B, I was saying that there's an extra step, right? So the extra step is actually to show that, you have to show, so either, so because they are symmetric, right? So either you want to show that this, the limit, the posterior probability of your lower limit is bigger than, this is true for any theta less than theta, the lower limit, or you can show the other one. Okay, right. So yeah, so because they're symmetric, right? So for any, if you draw it, right? So for any value which is, if this is your lower limit and this is your upper limit, right? So for any theta which is less than your lower limit, right? Then your posterior must be higher, right? Or so this is, in this case, your theta less than your theta L, or for your theta bigger than your theta L, for your theta L or theta U, sorry, should be lower and this should be upper, sorry, theta U. And for theta bigger than theta U, again, the probability, the density, so not probability, the density of your theta should be, theta U should be bigger than the density of your theta if your theta is less than theta U. So if you draw, right, this picture, then you're looking at this area here, right? So for any theta inside this shaded area, then the density should be lower than the density of your lower limit and your upper limit. Okay, because this is the barrier, right? This is the barrier, and because they are symmetric. Okay, so the density in the shaded area should be lower than the density inside the limit. Okay, so but because as he has said before, because it's symmetric, so you can just show one of these, either number 1 or number 2. Okay, so for example, if you want to show, right, that I want to show the second one, this one, right? I want to show is the theta should be lower than your theta of your upper limit. If your theta is bigger than your theta U, Okay, then you can start, right? You can start with, for example, you have your theta, if bigger than your theta u, right? So this is, I say you use your density, right? Because this is normal. So you have, right? Because you use the fact that it's actually symmetric. So you have this, because this is, so we're going towards our normal density, right? So we have, well, if you use, okay, I think you can use any function. So if you use mu or beta or whatever, it doesn't matter, right? Because it's normal. Okay, this is where you have to be careful because you put negative, right? So the sign will change. All right. Again, you put, and then you put your constant, which is your, okay, you have your, oh, right. Or you have your, and your exponential. Oh, no. Right, or less than, okay, my handwriting is again, right. Okay, so here, what happened here is, we have, you start with theta, we get a theta u, and then we have this function square, so it's still larger, but because you put the minus sign, then the sign become changed, right? You have the change sign, and then, but if I put exponential, the sign is the same because exponential is a monotonic function, right? So if I put exponential, this is a, right? Exponential a still less than exponential b because exponential is a monotonic function. Okay, and this is only constant. So the constant doesn't affect the sign also, right? And so this is actually your posterior of your theta, right? Is less than the posterior at theta and posterior at theta u. Okay, right. So this is what I meant by you can show by using the PDF directly. Okay, so this means that we can show that for any theta which is larger than theta u, right? We show that the density of your theta will be less than the density at theta u. Okay, and because this is symmetric, then it will be the same, right? So if you use your theta is less than your theta L, your lower limit, then we can also show that your theta, I mean, if you use it because it's symmetric, right? This one will be larger than your theta L. Okay, right. So any question about this?
I have a question actually. For this problem, right?
Yes.
Professor, can you scroll up to the graph with the density? Because I was thinking why. I was thinking the problem was asking something like, okay, imagine theta L, for example, shifted to the left by, for example, and a small epsilon 1, and then theta U shifted to the left also by a small epsilon 2, for example, right? But preserving the area to be density. This is asking whether or not the length theta L minus theta U is longer, right? Because if it's less dense, you need more coverage.
This is the height. This is the density actually.
Yeah.
No. They cannot be shifted. Okay, they cannot be shifted because it should be the highest density region. So the height here it means that the height here, I could change the color. It means that the height here, okay, right, go down. The height here is actually higher inside the region than outside the region. Okay, but you also must preserve the size. So it should be the size is 1 minus alpha, I guess, because it's just 95%. So the area here is actually 95%. And because they are symmetric and unimodal, the size on the left and the right is the same. So the height is the same.
Yeah, but for the HDR, okay, I understand that for the credible interval is symmetric, right? But does the HDR interval necessarily have to be symmetric also? 95% HDR.
No, this is because this is a normal distribution. In this question, it's a normal distribution. That's why it's symmetric. It's not because of the CI or HDR. This is why because this question 2 is about the normal. The normal is symmetric and unimodal. So if you change a different, like in our lecture, right? If you change a different distribution, it might not be the same.
Oh,
it might not. So it does not. It's not because of HDR. It's because of the normal distribution, which is symmetric. So this is because it is a normal.
So if for example, okay, this method, right, it depends on the symmetric nature. Okay, suppose that we have a unimodal distribution, for example, the beta distribution. Can we cannot use this argument, right? You can?
No, beta is not symmetric.
Yeah, so we cannot use this argument about
No, it's not, yeah. You cannot use this argument.
Yeah, I was thinking.
Yeah. So this is only okay. This argument is only because this one is because this is a normal PDF.
Yeah.
So you can actually use it for the T distribution. T is okay because T is unimodal and symmetric, right?
Yeah.
So T can. Right,
because I was thinking for normal, I think it's almost obvious. I mean, although we have to show algebraically why, right? But it's almost obvious that you can only go if it's supposed to be a symmetric distribution, there is no way for it to be even shrunk, right? I mean, to maintain or expanded to maintain 95. So I think yeah. But that's the thing. I was thinking for a unimodal distribution, right? We have to show that unimodal but not symmetric distribution. We have to show that shifting the distribution to maintain 95%. I don't know that that is not. It's more complex.
I think the thing is, as long if it's unimodal, even though it's unimodal, but as long as it's not symmetric, then you cannot. It's hard to show that.
All right. Okay. That's why I was going on the more general approach, and I feel.
No. You cannot generalize it actually because it must be as in the lecture, it must be unimodal and symmetric.
Yeah. So I was thinking the question was asking if you find any other interval, right? That prove that this is the best possible. Yeah, but that approach is wrong, right? Because
it's not actually. Yeah, because I think the approach is because this is because it's a special case of the normal, right? But I think for different distribution, then like even though it's unimodal.